So my first question, power converters that I've looked at already regularly achieve 96% efficiencies, and I've heard that with SiC you might gain an extra 2%. Doesn't that mean that all that effort that you've been putting into SiC development the last 10 years has been a waste of time? What do you say to that?
Yeah, doesn't it makes it sound like it, right? I made a 1% improvement in efficiency. It was already so high. Now, I think the big thing here is reducing power losses so you can make your system smaller, better, lighter, and do new things with it, right? And so when you look at it from that point of view, take a car, for instance, the traction inverter in a car, if it's a 200 kilowatt inverter and you save 1%, you're talking about saving 2,000 watts. Wow. 1% may not sound like a lot, but 2,000 watts of heat removal from a little tiny inverter that you're trying to shrink, maybe put around the motor of a car, that's a big deal, right? You can do new things. And this applies to all kinds of things, whether it's data centers or all kinds of power electronics. So maybe we start talking about how much power we save instead of how much efficiency we gain.
Yeah, exactly. I think that's a very good point. And I think to understand that, one of the things that we need to maybe first discuss is the differences between a silicon carbide MOSFET and a silicon MOSFET or an IGB device, which is obviously the devices, the power devices that you're targeting to replace. So what are the key differences there? And what are the benefits that the development engineer, the power converter engineer is gaining?
So let me see if I can share a picture that might help you guys visualize, what the differences are between these devices, and in particular also what then we make. Let's see if I can figure this out. Share screen. Okay, that's pretty nice and well organized. Yeah. Okay. Tell me if you can see the screen, and then I'll point out what we're talking about here. I think a lot of the user base understands that, at the 1200 volt node, silicon IGBTs dominate. There's a picture of a trench-based IGBT here that I'm pointing to at the left, a picture of a silicon carbide MOSFET, and then a picture of a silicon carbide trench JFET, right? And when you use the IGBT, the resistance, if we try to make a MOSFET at 1200 volt, it would have a very, very high resistance. This just comes from the fact that in silicon, because the critical field for breakdown is so low, you have to use a much thicker voltage supporting region, and you have to dope it lightly, which means its resistance tends to be high. And to cut that resistance, the technique is, you inject electrons and holes into that region so that it'll have a low resistance. But then once you do that, in every switching cycle, you've got to move the charges in and out, right? Which ends up slowing down the IGBTs. So if you wanted to switch high voltage devices very quickly or losslessly, this is where wide bandgap devices come in, because with their high critical field, like 10 times higher critical field, you can theoretically have, a 10 times thinner region to support the voltage like I'm showing here. It's called the drift layer. And then there's no need to inject carriers anymore. So you're just charging and discharging capacitances. And this allows these devices to switch much faster. So that's the whole value proposition for wide bandgap devices. And the trench JFETs, that we make are used in cascode form to kind of do the same thing. So we'll talk more about that later. But the key point I'm making is they switch a lot faster. And so we're going to get into, well, that's all good, but they also create a bunch of problems for people when they switch a lot faster. And then this other point that people get, especially the people focused on traction inverters, is that, well, then the IGBT has a knee to its conduction characteristic. You have to first turn a PN junction on before it'll carry any current at all, compared to a MOSFET, which is linear. It's like a resistor through the origin. Yeah. And so if you're operating at modest currents, which in an EV, for example, in the traction inverter, you are most of the time, many applications are like that. You don't need to waste all of this conduction voltage drop. That's just dissipation in the power switch. But I think the main thing you'll be interested in discussing later is, well, okay, it switches fast. So how do you handle all of that fast switching? And it's kind of, this is another picture of what happens at the lower voltage node, where the main dominant device in the market today is the silicon superjunction. Then your other guest will talk about gallium nitride hemp devices, which are very fast switching wide bandgap devices. And there's trench MOSFETs and planar MOSFETs out there made out of silicon carbide, and then our technology, right? And in a little while, I'll explain, why we chose this technology. It's fundamentally because it allows you to make the smallest silicon carbide chip for a given resistance, which then cuts its capacitance, which then allows it in a cascode to switch very, very fast, right? And so fast switching may be good for power losses, but we'll talk more about, then what challenges people face when they try to use it.
So when I'm specifying or selecting a silicon MOSFET or maybe an IGBT, I have certain sort of parasitic parameters that I have to consider. With a MOSFET, one of the things I'm going to be looking at is probably the RDS on in order to minimize the on resistance. With an IGBT, it's more I think it's the voltage drop over the collector emitter that's sort of my concern, which is an equivalent resistance almost. How do SiC MOSFETs stack up with those parasitic parameters that are so important to me with the previous silicon technology, such as also the capacitances on the inputs and outputs?
Yeah. So I think, if you want to answer the question about resistances first, at this point, silicon technology is pretty amazingly good because, I have this chart here, which I use to track the breakdown voltage rating of parts and what resistance they might deliver if I had 1 centimeter square of that chip size available to me. And, this is a line that represents the theoretically best number you can achieve with basic device structures in silicon. But because silicon uses the superjunction technique, it's now well below that limit. These two stars represent silicon devices. So at the 650 in the 650 volt class, they're down near 7 milliohm per centimeter square. So 1 centimeter square of chip would give you a 7 milliohm device. These yellow dots represent some of the best GaN devices. These black ones represent some of the best silicon carbide MOSFETs. You can see they're making big jumps because this is a logarithmic scale. The silicon carbide devices, MOSFETs, are down near 2, and some of our latest cascode-based technology is down near 0.7. Right? This is the generation 4 stuff that we launched a couple of years ago. And what this boils down to is that, for a given targeted resistance, you can get a lot more die on a wafer with the technology that brings you the lowest resistance per unit area. Then you can use this to fit it. You can use this to fit it into smaller packages and whatnot to cut inductances, which is part of switching fast. But, one fundamental thing is that once you start having small chips and reducing capacitances, all these parts get extremely fast in the way they switch. And then you have to manage those parasitics. But the fundamental reason we are doing this is that it leads to more cost-effective devices, but more importantly, fundamentally, the capability to be very fast in switching. Then you can take it and do with it what you need. Sometimes we have to just slow the devices down because of the challenges of fast switching.
Yeah.
Does that kind of answer some of your question?
Absolutely. Yeah. No, that's great. And so, another sort of area of interest is obviously then to understand which applications benefit the most from silicon carbide. When we look at maybe some of the marketing material that's shared by the semiconductor industry on wide bandgap devices, we get the feeling that silicon carbide is very robust and maybe more appropriate for higher voltages, let's say above around 650 volts. Whereas GaN is more suited to higher frequency switching, but maybe below 650 volts. Is that what you see in the way you advise engineers who are looking to benefit the most from SiC?
So what I'd say is that gallium nitride silicon devices are still quite popular. In fact, dominate the market. And then there is, of course, we compete with silicon carbide MOSFETs a lot more than we do with gallium nitride devices, probably because of the type of split in applications that are being served. So I thought I'd give you the perspective on the kind of applications where we definitely see a lot of uptake of our silicon carbide devices. And in most of these places, I think the dominant competitor is either a silicon device or a silicon carbide MOSFET for us these days. So, you've heard all about the automotive. So the traction inverters, onboard chargers, and DC-DC converters. This is probably the biggest segment. But the segment that's the oldest for us is just regular battery chargers for forklifts, industrial automation, those robotic chargers in big warehouses, those kinds of applications. Including nowadays, there's some wireless charging work for big commercial vehicles. IT infrastructure just basically means telecom, base station rectifiers, or server power supplies. This is an emerging and growing area because that totem pole PFC topology that eliminates the input diodes is really gaining quite a lot of traction now. Took a long time, but it's getting a lot of traction, and it's used a lot in the onboard charger. That same topology. And then I think so. You've always known that silicon carbide had a role to play in the renewable space, especially in PV. But we see a lot of uptake in the energy storage sector. So one common thing you'll observe here is that everything I'm talking about, 1.5 kilowatts or so is the low end of power. Most of the stuff is, 6.6 kilowatts in OBCs, 11 kilowatt, 22 kilowatt, high kilowatt space.
Yeah.
So maybe that's the reason, where the applications are being served by these high current discrete devices. And in the future, even higher power applications served by a lot of modules. The last category is interesting, circuit protection. So we are seeing a lot of interest now with, there's so many different DC sources. There's a lot more interest now in making circuit breakers that are solid state, that don't arc. There's no arcing. And not just that, actually, even industrial breakers, normal AC breakers, there are specialized applications where being solid state may bring great benefit. So they're having technologies that give you very low on resistance in this 1200 volt class and so on is very useful because circuit breakers carrying current all the time and wasting heat. So these days we are trying to get into the sub-milliohm class in this space. So you can talk about resistances of the kind you get from two metal contacts touching each other.
Yeah,
they give you a sense. I think it's mostly we see the power area that we serve is relatively high. So maybe that's the kind of segment where you see more high current vertical silicon carbide devices. Yeah. And I think possibly a lot of the lateral GaN devices have already penetrated a lot in lower power. Definitely in your wall chargers. See them all.
So when it comes to an application, if I have an existing design that is silicon MOSFET or IGBT based, and I move that design to a SiC-based solution, what am I going to see in terms of improvements, in terms of, say, weight, volume, efficiency? What should I be expecting to achieve?
Right, that's a really great question. If you're designing a new system and you're trying to choose between an IGBT and a wide bandgap device, you do a bottoms-up job of doing the design for these fast switching devices. You can get quite a big bang for your buck between, if it's an IGBT, between the conduction and the switching losses, right? I think I have somewhere down here, maybe a table of numbers I computed a long time ago for, what happens in a traction inverter. If you could ideally use, I don't have it handy, but it's like a 3x reduction in losses that's possible, power losses that's possible if you use a wide bandgap device, because less switching loss, less conduction loss, right? And so that's if you do everything by the book. But typically, what happens if you are just trying to upgrade an existing design, you have to deal with these very, very fast switching devices. I'm just showing a picture of how fast some of these devices switch, and so the act of managing that and managing the EMI means that depending on your constraints, you may have to give up on some of the performance benefits here. So this is where, this meeting that you're having is very pertinent. It's just to find out, let's talk about what you can really do. It depends a lot on your constraints. If you're just upgrading an existing design, doing a bottoms-up new design, what are you willing to do?
Yeah.
How much?
I was going to say that's an interesting point. So obviously over the years, if you attend any of the congresses, for example, that are looking at and investigating power converter and power inverter technologies, there's always a lot of research going on into different types of topologies for your power factor converter, for DC and AC to DC converters. If I have an existing design, does it even make sense to just replace the silicon devices with silicon carbide, or would it make more sense to really look at the topologies I'm using for each stage and maybe consider a redesign in order to really get all the benefit out?
Ideally, if time to market was not a problem for you, you would go, I would recommend you do a bottoms up design and get the full benefit out of these parts that you're buying. Shrink your system, cut the cost, make it more efficient and more robust, whatever thing. You even get more voltage margin for your products and cut their failure rates in the field. All kinds of things can be done. But that's a choice that I find in the real world doesn't actually exist for most of our users, because they have projects they need to deliver quickly, projects for which they have platform developments for the future that have more time. So it's the whole mix. We actually got started out because it's what we make is a cascoded device ultimately. And in that device, let me show you a quick little picture of what it is. Inside there's a specially designed silicon MOSFET with a 5-volt threshold that is switching this depletion mode JFET. So from the outside, you operate it like a 3-terminal device, right? So because the gate drive is ultimately, all you need is 0 to 10 volt to drive it, right? But it can be compatible with all other kinds of gate voltages that you get, whether you're driving a silicon carbide MOSFET or an IGBT. So our generation one products, many years ago, the first thing actually they did was replace IGBTs. Now, it was not easy even then. You had to put extremely large gate resistances and extra gate capacitances because, you're replacing a device that's far slower. But it was a thing that people did. And when that happened, they immediately got some efficiency benefit without making massive changes to their platform. But as the years have gone by, there's more and more designs that are really all focused around wide bandgap devices. So they are generally better done, better equipped to deal with the fast switching. And, so there's a better chance of fully exploiting all the benefits that we are bringing here.
Yeah.
But still, you saw the packages I showed you for the kind of products that dominate the actual business as we do it today. Many of these packages are really old school silicon packages. They have a lot of parasitic inductance.
Yeah.
Therefore, the devices are used and switched significantly slower than they would otherwise be. Right. So this is what, it's an evolution in the design and practice in the world of power electronics. So a lot of these old packages are being used. They are now being used a lot faster than IGBTs used to be switched, but they're still the old packages. They do have a lot of inductance. So they bring, they cause a lot of overshoots and whatnot because of their inductance. And so, with our device structure, we often recommend small snubbers because they really help to tame under these extremely fast changes of current, how much overshoot you'll get and how you can manage all this.
Yeah.
There's a lot of education required for, switch it this way. In our case, it's not so much the gate driver that's the problem because it's a cascode. It's very flexible on the gate drive side, even for DSAT protection. All of that just works like IGBTs.
Right.
The big thing is the cascode is it's a bit harder to control the switching. So we use these tiny surface mount snubbers that dissipate very little power, 1/4 watt, maximum 1/2 watt, to manage these waveforms and get it to all work, because the devices people are still using come in highly inductive packages. It's good you're asking about these real world challenges because that's the situation.
You raise a very interesting point because that's one of the challenges of the semiconductor industry. One of the semiconductor industry challenges is not just the development of new semiconductor devices, but also the packaging that goes with it as well. There's a lot of work that goes on to develop new types of packages, and that's not always purely an electrical task. It's also a mechanical task as well, isn't it? It needs to be you need to be able to pick and place it. You need to be able to solder it, and it also needs to survive the challenges of the environment it's going to be put in. Is this another area that you're looking at United SiC to improve the package technology?
All of us device suppliers in GaN, silicon carbide, are looking at better and better packages. One of the challenges we face in deploying new packages, I think you understand very well, is looking at how the supply situation has evolved in the world. People are afraid of packages that come from only one source. They really want this to be something they can get from multiple sources. And so the evolution of packaging standards, is it's unsatisfactory. It's kind of slow. There are not well-established standard packages that you can get from other people, many suppliers, in a standard footprint that would make the user base much more comfortable with jumping to new technology. You finish the design, at the end of it, you have to manufacture it. So you've got to be able to convince your company that you've picked the best component within the constraints of actually being able to get it and manufacture it.
Precisely.
But the new packages are all coming. They are somehow delayed, I think, by the lack of how long it takes, not the lack of how long it takes us to agree on standards.
Yeah. Now, I think that's always one of the big challenges of the electronics industry is defining and agreeing on those standards. I don't think it matters if you're trying to define a wireless protocol or a new package or a new manufacturing process. I think that's what holds us back a lot of the time. I'm just going to turn now to our audience and have a quick look to see who's online today. So a quick hello to H. Pratt. I remember the name joined us last time, and Annie and Jenny as well joining us today. Don't forget, if you've got any questions, feel free to pose them to us via YouTube, on LinkedIn, and also on Twitter using the hashtag ElectorEI for Elector Engineering Insights. I've just got one more question for you, Anup, before we take a look at GaN technology as a comparison. One of the questions I had was regarding the manufacturing process. Obviously, we're used to how silicon devices are made. We've got a nice silicon wafer as a starting point, and then we build up in layers on top of that. Are silicon carbide devices made from a silicon carbide wafer, or is the manufacturing process different to how silicon devices are manufactured?
There's a lot of similarities. You start with a single crystal silicon carbide wafer. It's just that silicon carbide wafer comes from a boule which is just this big compared to a silicon one that is enormous. So that affects how much the starting material costs. It's much harder to create. And then it follows the same process. You grow an epitaxial layer on it, which is the layer that supports all the voltage in this device, in a vertical current carrying device. Silicon guys, we did that in silicon, we do that in silicon carbide. It's much harder than silicon carbide because you do it, instead of at 1000 C, you got to do it at 1550 or 1600 degrees Celsius. That's about the melting point of silicon. And then it's grown to a lot more defects, and the material is much more imperfect compared to silicon. It's very good now, but it's evolved a lot, but it's still not silicon.
Yeah.
Then after that, it's got to go to the fab, and in the wafer factory, if you look at a silicon carbide wafer fab, it looks just like the silicon wafer fab for the most part. It just has a few extra tools in it to assist with the fact that you've got to implant at high temperatures, you've got to anneal those implants at a very high temperature, but overall, it looks quite a lot like a silicon line. Might have some few specialized tools at the back end of it. Ultimately, some of the process steps in silicon carbide are lower in throughput than silicon, and therefore the wafers tend to cost more for that reason. At the end of it, though, like I described to you here, I showed you a picture where the resistance that we get, out of a centimeter square of chip size, was this a chart? Yeah, is so much lower than silicon devices that, we get so many more die per wafer if you're trying to target a certain resistance, that I think at this point we are able to be fairly competitive with superjunction type MOSFETs, despite the higher cost of building silicon carbide. But the factories look, the fundamental steps are rather similar. Factories that do the actual processing of the wafers look pretty much the same.
Super. Well, thank you very much for all those insights, Anup. Now, go over to Denis from InnoScience. I'll just add you to our stream and take that out for you. So, and we'll come back to you later, Anup, with a few more questions. So, Denis, welcome to the show. Thank you for taking the time to join us.
Yeah.
Now, we're just talking to Anup about SiC, and silicon carbide devices are called silicon carbide MOSFETs, which obviously relates similar back to the silicon MOSFETs we're used to. But when I look at documentation about gallium nitride, we talk about gallium nitride transistors. Is that correct?
That is correct. Actually, to be more precise, is a high electron mobility transistor. So the magic of GaN is that you have an heterojunction between argon and GaN, and you have a spontaneous formation, an electron gas, which owns, let's say, very high mobility. All the benefit of GaN, let's say, is coming from that high electron mobility that you intrinsically have. So it's a lateral device, allow you, let's say, to switch fast, and it is a wide bandgap material, so it can handle, let's say, high voltage.
And is it, if I were able to look under a microscope and actually see it operating, does the material inside the transistor actually turn into a gas during operation, or is it just a term we use to describe the physics that's going on in there?
It's really the factor, yeah, it's not that you see a gas, let's say, but it's the fact that you have a confinement of your channel. It's an electron, is exactly the channel of your device. Perhaps let me also do the trick that my colleague did. If I show you just one slide, actually I have prepared it here. So you see the magic, you can see my screen, right? Yeah, so the magic is happening here on the heterojunction between argon and GaN. You have the spontaneous formation of the two-dimensional electron gas. That is coming from that.
Okay, so super. It's good to clarify that, because it's just obviously a very different functionality to a typical silicon-based device, and it's interesting to clarify that. Yeah.
Yeah, actually, it is similar to a silicon device, because once you have your channel that is spontaneously formed, that's why naturally these devices are normally on. Then basically with your gate, you are able to deplete the channel locally here by modulating the gate and interrupt the conduction. So it's, let's say, is like a normal transistor, but the threshold normally is negative. That is why this is what we have been engineering over the years, is to have what we call normally off operation, where basically by doing some trick on the material, let's say, you're able to have a local depletion of so locally interrupt the two-dimensional electron gas, and therefore realizing normally off operation, let's say.
Okay, so we've got the gas element of GaN devices, and we've also got they're normally on, and you've made that change. What are the other differences that we would expect to see between a silicon MOSFET and a GaN transistor?
Yeah, the other small difference. So if we look in the performance, we see the capability of GaN of switching a higher frequency than silicon, and this one enable all new sort of application, or more like, let's say, increasing the power density of the converter. This is one. The other big difference with respect to silicon is the very low reverse recovery, which I show you here. Basically, GaN, since you don't have a PN junction, you don't have reverse recovery current, which is, let's say, cause issue in possible system in terms of power losses. So this one, I would say, is the difference. The other big difference that people need to get used to it is on the gate voltage swing. Normally, silicon MOSFET or even silicon carbide MOSFET, you can have a gate swing up to, let's say, plus 20 volt, plus 15 volt. With GaN, normally you are limited to 6.5 volts, 7 volts. That's why there are drivers made for GaN. But other than that, let's say, it's a better device, is switch fast. You just need to know how to handle it.